Hello guys, today I will present about electricity and magnetism. Let's go! Here is the table content. We have two, which is vector calculus, and the second one is coordinate system. To solve electrostatic problem, we first need the right mathematical language, which is beta analysis. Beta analysis have two components, which is scalar and vector. Scalar quantity like electric charge Q or potential V has magnitude only, while a vector quantity like electric field intensity E has both magnitude and spatial direction. For the vector multiplication, we manipulate vectors using two co-products. The first one is the dot product A dot B, which project one vector untuk another to yield a scalar. And the second one is cross product, which yields a vector perpendicular to both. Finally, field calculation becomes infinitely easier when we match the mathematical symmetry to the physical object. We choose Cartesian coordinates for rectangular shapes, which is x, y, and z. Cylindrical coordinates for line or cable, which is rho, v, and z. And the last one is spherical coordinates for point sources or spheres, which is r, theta, and phi. Fine. Now we move on to the part 2, which is the differential operators in vector calculus. In this part, we use differential operators to examine how vector fields vary across space using the del operator. The first one is gradient. The gradient, which is delta V, acts on a scalar potential field pointing in the direction of maximum increase to generate a vector field. Next one is divergence, which is delta dot A, measures whether a point acts as a source of swing by calculating outward flux per unit volume. In this divergence, we will use a dot product. The next one is curl, measures field rotation of circulation around a point. In this curl, we will use a cross product and will have a matrix form. Lastly, combining divergence and gradient gives us a Laplacian, which is delta square V, which forms the basis of Laplace and Poisson's equation in potential theory. In this Laplacian, we need to have a 2 times of differentiation. Now we move on to the part 3, which is the fundamental vector of integral theorems. To bridge microscopic differential behavior with macroscopic physical system, we rely on two core integral theorems. The first one is the divergence theorem. The divergence theorem states that the total outward flux of a vector field through a closed surface equals the volume integral of its divergence inside that volume. The second one is Stokes' theorem. Stokes' theorem states that the circulation of a vector field around a closed loop equals the surface integral of its curl over the bounded surface. These theorems allow us to switch seamless between field differential equation and integral measurements. Move on to the part 4. Now we transition into physics. Electrostatics studies static electric charge. By Coulomb's law, a charge Q produces an electric field intensity E defined as force per unit test charge. In free space, this relates to electric flux density D through permittivity epsilon naught. Real-world engineering systems rarely feature isolated point charges. Instead, charges are distributed continuously, with some differential charges dq over d1 lines using line charge density ρl over 2D surfaces using surface density ρs, or over 3D volumes using volume density ρv. Now let's go to the part 5, which is Gauss' law, potential, and conservative field. Calculating E via integration can be complex, but Gauss' law simplifies this for symmetrical geometries. It states that the total outward electric flux through any closed Gaussian surface equals the enclosed charge Q ENC, which is Q enclosed. Because electrostatic fields are conservative, moving a charge around a closed loop requires zero network, which is E.dl equal to 0. This conservative property means the electric field can be expressed purely as the negative gradient of a scalar electric potential V E equal to negative delta V. This let us solve scalar potential problem first, then take the gradient to find the field. Last but not least is summary Maxwell electrostatic postulates. To summarize, vector calculus provides the complete mathematical framework for electrostatics. Divergence connects flux density directly to charge sources, which is delta dot D equal to rho V, while curl proof electrostatic fields are non-rotational, which is delta cross product E equal to 0. Together, this form Maxwell's fundamental equation for electrostatics field.